Hi there, this is JNEL, and if you didn't watch Lesson 1, that means Jacob Nash Engineering Lessons. But you can see that because that's what it says on my account. So this is Unit 1.1, Lesson 2 on levers. That is the first listed simple machine in PLTW. So the first thing is that there are 3 different kinds of levers. So here's what the first kind might look like. So that this might be a beam, and then this triangle is the fulcrum. So we can label that with F. Then we have for a this is called a first class lever, first class. And so right here would be the resistance force, and then over here is the effort force. So an example would be a seesaw, or some people call it teeter-totter, but I just call it seesaw, so whichever one. But if you know what a seesaw is, there's effort that's being put on there. So if someone's sitting on there, so let me draw that again. If somebody is sitting on there, if that's a person and they're sitting on there, there's effort down. But if this side goes down, this side's going to want to go up. That's the resistance force. And that there might be another person on there right here. Then when it goes back, the forces switch. But it's all based on the fulcrum that's right there. So, that I explained more about what effort force and resistance force are, but the effort force is described as Fe with a subscript E that is small below, and then Fr is resistance force. Ooh, that's messy. Sorry about that. Let me draw that better. Okay, so that is a first class lever. So now there's also second and third class levers. So here's what a second class lever might look like. So we have maybe a beam right here, and then the fulcrum's this time over here. So this time that couldn't be a seesaw, because we know that if that fulcrum is all the way over there, then it would never be able to go up and down. Like, it would just go right down right away. And on a second class lever, the effort force is at the end and below it, and the resistance force is at the top but in the middle. So if you can think of an example of this, try to think of it. And there are a few, but one example is a wheelbarrow. So instead of it being a triangle, it would obviously be a wheel. And then don't know if I can draw this very good. So that would be the part where you put things in it. Oh, duh, the wheel would be over there. Sorry. Then, yeah, never mind. That would be facing a different way if I was going to have the wheel there. Sorry about that. This thing takes a long time to erase. But, so the wheel, if it was right here, then instead the section where you put stuff in it would be right there, and then the handles would be right there. And so the effort force is right at the end. You know, that's what you have to use. You have to use effort to use those handles and pick it up. And then the resistance is right here. And why it's in the middle is whatever you put in it. So if you put some like boards in it or something, that keeps it down. So remember, The effort force is what someone might do to the simple machine to try to get it to do what it's supposed to do. And then the resistance is whatever force, it helps it work properly, but it makes sure that things don't go crazy. Because obviously, if there was no resistance on a seesaw, it would just, I mean, that's just an impossible situation. Like, it couldn't be down, it would probably just like snap in half. And then with the wheelbarrow, if there was no effort keeping it down, then it would just fly up, I guess. I mean, there's gravity, obviously. So, anyways, that's second class lever. Now, third class is, if this was a beam, okay, why is it drawing dots? Sorry about that. Don't know why I was doing that. So, once again, the fulcrum is at the end, but it's a little bit different this time. So this time the effort force is in the middle. And then at the top there is resistance force. Now it's a little bit harder to come up with an example of what a third class lever would be, but I think a good example is tweezers. So let me try to draw that. So you got one side of the tweezer right here, and then the other side right here. And let's just say this red dot is what thing you're trying to tweeze or whatever. So the effort force is right here because you are squeezing it. And to be honest, it's also right here because you're squeezing both sides. And then on the top at the ends there's resistance right here. And then the fulcrum would be the part where both like tweezer stick things connect. I don't really know what that's called, like handles maybe. So once again, you need the effort force because that's how you can tweeze or squeeze it. And then you need the resistance force because if there was nothing as a resistance, then those things would just like go right past each other and it would just like fall off, I guess. So now you know why you need both of those things. And so that is, oh wait, that's not it, sorry. I thought that was the end of the video, sorry about that. So now we can use an example of how you could calculate AMA and IMA of levers. So first, let's take an example for IMA that I have here. Let me see. So, IMA. And if you don't know what IMA is, you need to watch lesson 1, because I said what it was. Okay. So, if we remember, that is dE over dR. So, if you notice, I only said what FR and FER, like the resistance force and effort force. So, there's also resistance distance and effort distance. And that's what you use to calculate IMA. And here is, oh, it's doing that thing again. The stylus doesn't seem to work that good. So here we have a lever, and this time the force resistance is over here. Resistance force, sorry. And effort force is over here. So that means that it's a first class lever. So, like a seesaw. So, now, let me try to think right here. Okay, so, hold up a second. So, as you can see, I had to redo that because something I was looking at, an example problem something was wrong with it. I don't know what that was, but I had to redo that. So, here we have it's still a first class lever. It just maybe looks a little bit different. So, how you can tell, once again, is that the fulcrum's right here, and then this is the resistance force, and then this is the effort force. Now, you can see that I've circled in different colors what certain things are. And we can find both of these, IMA and AMA. So, I talked about what the forces are, but the distances I didn't yet. So, right here it would make a right angle, and if you can see that, and then also right here. And yeah, that's a little messy, sorry. But that's how you know what is what. So really, if I didn't outline these colors, if I only had the forces up, you could tell me what distances they are. Because here we have the effort distance, and then we also have, or sorry. Oh, I actually did that wrong, sorry. Here I go again. Let me try to erase that. I'll just erase this whole thing. That's messed up. So, the resistance are by each other, and also the effort factors are as well. So let me do that again. So that should be here, and then that should be here. So they make a right angle with each other, the two areas right there, and the points, really. These are the points at which the forces are at. So we can calculate the IMA and AMA. Let's first do the AMA, actually. So we know it equals FR over FE, and so FR, that is 80 pounds. Oh, I thought this was charging. There we go. Over the effort force, which is 65 pounds. So, any engineering class that you're going to take, teachers always are going to want you to have the units if you need them, or not if you don't need them. So in this case, you don't need them because they cancel out. If you divide two units, they cancel out. So we can X out the pounds because they're both on top of each other. Now we can just divide 80 by 65. Or sorry, hang on. 85, or sorry, I messed up again. 80 divided by 65. That is 1.23 approximately. And so that's all it is. The AMA would be 1.23. And you don't need to have any units because they canceled out. And if the mechanical advantage is greater than 1, then that means that it requires a small effort force. Is the effort force small? Well, compared to the resistance force, it pretty much is. So that's why it would turn out that way. Because you know that when the number is greater in the numerator, then it would usually make the answer, if not always, greater than 1. And it is the opposite if it's less than 1. So now we can do the IMA. So we do DE over DR, and it's both 6 feet. That seems to be the magical number these days. But so all we have to do is 6 feet over 6 feet. And the feet cancel out, and we know that 6 divided by 6 is 1. So that's what the IMA is. AMA 1.23, IMA 1. Now we can see what the efficiency is now. So, once again, AMA was 1.23. And then the IMA is 1. No units on either of them. So the efficiency formula is, so percent E equals AMA divided by IMA, in parentheses, then multiplied by 100. So let's do that. That's not that hard. AMA is 1.23. IMA is 1. So first of all, anything divided by 1 is itself. We know that. So now we can just do 1.23. Multiply that by 100, and we get 123%. So this seesaw first class lever is 123% efficient, and that is good. And you might, if you come up with an answer like that, you might think, oh, that's over 100%. How's that even a thing? Well, that can happen, but the typical rule is that if the efficiency is greater than 50%, then it's a good simple machine. And really what caused us to be that efficient was just the forces implied and the distances. So obviously, since it was 6 feet for both of the distances, that would make a good seesaw, because if it wasn't like that, then it would completely be off balance. So that's why it came out that way. So I think that is all now, yes. So thanks for watching, and see the other Simple Machine videos on the channel under playlist. Thanks for watching.